let's do some science. I've got my normal College Station tap water, and I've got my son's little rubber ducky. Now when I put this little rubber ducky, in my water, what do I get? I get it lighting up. Very, very nice. So it turns out that if I look at the bottom, this kind of tripped me out the first time I saw it, because I thought they were normal rubber duckies. If you look, there are two electrodes on the bottom of them. One of them is just normal metal, and the other one is rusted over. What do you think? I think it has oxidized just a little bit or rusted, and it's reacted with oxygen. Very good observation, which will be important later video. So the reason why this is actually happening is that what this tap water is an electrolyte, because it has some impurities dissolved in it, something like calcium or magnesium or some other kind of metal ion is now dissolved in this, which is able to conduct an electric current. Let me be clear that pure water is a non-electrolyte. This is tap water, so it works. I don't have any pure water at my house. All I've got is the tap water. So watch out. A lot of people think that an electrolyte gives you energy, because I think they think because they drink a sports drink, which they advertise as giving you energy, and they advertise that it has electrolytes. So you think that energy and electrolytes are the same thing. That's not the case. That an electrolyte is a medium for the energy, which means it provides an environment for the energy to pass through. So as you can see, it passed through from one electrode to the other electrode. That's what an electrolyte is a medium to pass through. So now we know what an electrolyte is, we can now further our understanding of solutions. Remember, solution is always a homogeneous mixture. If it's not homogeneous, it's not a solution. Also, please remember what a solute and a solvent are. The solute dissolves in the solvent. That means an example would be salt could be a solute, and it dissolves in water, which is the solvent. That's something that goes into something else. I showed you what an electrolyte is, and there's a difference between a strong and a weak electrolyte. The definition of a strong electrolyte is it ionizes 100% all the way, straightforward all the way, and none of the way back. The weak electrolytes will go forward just a little bit, but they will actually come back in a little bit more. That's called an equilibrium, and that's another chapter, another video. So to be clear, we won't be testing on equilibriums in this chapter. We'll only be testing on weak electrolytes. You may remember this scientist, Svante Arrhenius, because he was the one that I told you about the Arrhenius definition of an acid, where that if an acid started with an H and the bases ended in OH, well, that was because they would ionize completely, right? They would ionize into the H plus, and acids would ionize to the H plus, and bases would ionize to the OH minus. So he was the first person to really come up with this idea. Also, when we look at a solution, we can get an understanding for how much solute is dissolved in the solvent by looking at its solubility. That means what point it would be saturated at. Different solutions will have, different solutes will have different solubilities, and we'll get into that in detail in chapter 16. Just know that you could see these units here. Strong electrolytes break down into three different flavors. Mr. Russell, I only see two. The third one's coming. Okay, the third one's coming. So soluble salts, which is most of them are soluble salts, are strong electrolytes because they're ionically bonded. Strong acids, those are the ones that you will have to memorize. The three most common are pictured here: HCl, HNO3, and H2SO4. Hydrochloric, nitric, and sulfuric acid um, are considered strong electrolytes. So you might be wondering, what is the third one? That would be the strong base. We'll get to that in another slide. Show how a strong acid like HCl would dissociate when it is dissolved in water. We would have to first come up with the net ionic equation. That's this thing, where we have taken our original HCl molecule and we have broken it down into two different ions, because that's what happens when it dissolves in water. Then I will assign assign these shapes to show that I would need to draw the shapes just like I've seen before, where these would be the reactants as they are together, and then they have been separated. It's important to notice that one circle is smaller than the other. That would be the hydrogen ion, because the hydrogen ion is actually much smaller than the chlorine ion. I love this picture because it shows a homogeneous solution of all the ions. This is a strong acid by the Arrhenius definition because it has the H plus ion. That's the Arrhenius definition of an acid, the H plus ion. Contrasting with the strong acids, we have the strong bases, which are also strong electrolytes. They will dissolve and will spread out homogeneously, much like the acids will, except now instead of creating the H plus ion, they're creating the OH minus ion, which you can see here. Those are those orange circles in the picture. Also, for a bonus safety, is that bases do feel slippery when they get on your skin. They are harmful to you, but they don't hurt immediately. So if you are working with a base and all of a sudden your hands feel really soapy or slippery, that's a good clue that you have some base on your hands. So I would recommend you go straight to the sink and wash your hands and get rid of it. If strong electrolytes ionize 100%, you might be able to guess that weak electrolytes ionize less than 100%. You may be surprised to find out that it is a great deal less. The acetic acid will only ionize 1% across. If this were a strong electrolyte, this would be a 100% over here. Please don't make the mistake of thinking that a weak electrolyte or a weak acid is not harmful to you. Even though vinegar is, you can actually drink vinegar and get away with it. If you had a concentrated acetic acid, called glacial acid, it is nothing to mess around with. It can kill you just breathing the vapors. Hydrofluoric acid is actually a weak acid, but it is still lethal. So you have to be very careful with that. Here's a picture of the weak electrolytes where 6 of the molecules have not broken up at all, but only one molecule has given away its H plus ion. So some of them will give away the H plus, but most of them will not. So contrasting with the weak acids, we now have the weak bases. Ammonia is a weak base. So please remember that ammonia is a weak base. Instead of producing the H plus ion, we're now going to produce the OH minus ion. This one will not go to 100%. I'm not sure how far it will go, but it's far less than 100%. And but to distinguish between a strong base and a weak base, the strong bases are the group have a cation that is in the group 1 or group 2. So all of the alkali metals or the alkali earth metals like lithium, calcium, sodium, those hydroxides are all strong bases. And notice that nitrogen is not in the alkali metals or alkali earth metals, so it is a weak base. Gotcha. We'll do this thought experiment in class, so come prepared to justify your choices and show the claim, evidence, and reasoning. Thanks.